An aurora, PL aurorae or auroras, B also commonly known as the Northern Lights, Aurora Borealis, or Southern Lights, Aurora Australis, C is a natural light display in Earth's sky, predominantly seen in high-latitude regions, around the Arctic and Antarctic. Auroras display dynamic patterns of brilliant lights that appear as curtains, rays, spirals, or dynamic flickers covering the entire sky. Elias Loomis 10 and later Hermann Fritz 11 and Sophia-Stromold 12 in more detail, established that the aurora appeared mainly in the auroral zone. The phenomenon known as the aurora borealis, or northern lights etudes. Its counterpart in the southern hemisphere is called the aurora australis, or southern lights, which similar features to the aurora borealis and changes in sync with the northern auroral zone. The pitch angle increases as the electron travels to a region of greater field strength nearer to the atmosphere. Thus, it is possible for some particles to return, or mirror, if the angle becomes 90 degrees before entering the atmosphere to collide with the denser molecules there. Other particles that do not mirror enter the atmosphere and contribute to the auroral display over a range of altitudes. Auroras undergo a transformation throughout the night, commencing with soft glows that gradually intensify into vibrant coronas, although they may not always reach this peak. Conversely, they tend to dwindle in reverse order. Until the 1960s, it was believed that these fluctuations were attributed to the Earth's rotation beneath a fixed pattern relative to the Sun. The mechanisms responsible for Steve are also linked to a distinct type of aurora that resembles a picket fence, although the latter can occur independently of Steve. This unique aurora is characterized by the precipitation of electrons in the atmosphere, but it manifests outside the typical auroral zone, at lower latitudes than usual auroral displays. When the picket fence aurora appears in conjunction with Steve, it is situated below it. 51 protons are also associated with auroras, both discrete and diffuse. The spectacular displays of auroras are caused by the release of light energy in the upper atmosphere, above 80 kilometers, 50 miles, as nitrogen atoms reunite with electrons and oxygen atoms and molecules return to their stable state. This process is triggered by the impact of high-energy particles that penetrate the atmosphere, which can include both electrons and protons. Christian Birkeland discovered that these currents flow in an east-west direction along the auroral arc, and subsequently, these currents, which flow from the daylight side towards midnight, were termed auroral electrojets, also referred to as Birkeland currents. Furthermore, the ionosphere can contribute to the formation of auroral arcs through a feedback instability process that occurs under conditions of high ionospheric resistance, typically observed at night and in the dark winter hemisphere. The planet Earth is perpetually surrounded by a stream of superheated, magnetized particles known as the solar wind, which radiates from the Sun in all directions as a consequence of its scorching 2 million degree outer atmosphere, the corona. Earth's magnetosphere is shaped by the impact of the solar wind on Earth's magnetic field. This forms an obstacle to the flow, diverting it, at an average distance of about 70,000 kilometers, 11 Earth radii or Re, 61 producing a bow shock 12,000 kilometers to 15,000 kilometers, 1922. Meanwhile, Earth's 23-degree axial tilt causes its geomagnetic pole to shift daily, altering the angle at which the planet's magnetic field interacts with the incoming solar wind throughout the year. This complex interplay can lead to subtle, cyclical fluctuations in the way the solar wind engages with Earth's magnetosphere, ultimately affecting the likelihood of intense auroral displays. Recent studies have also revealed that individual substorms may be interconnected, forming a network of correlated events. As electrons move downwards through these forces, they gain a significant amount of energy, amounting to several thousand electron volts, in the direction of the magnetic field lines, heading towards the Earth. This acceleration, which is parallel to the magnetic field lines, reduces the angle of all electrons passing through the region, resulting in many of them colliding with the upper atmosphere. Unlike the scattering process that generates diffuse auroras, the electric field boosts the kinetic energy of all electrons moving downwards through the acceleration zone by the same amount, transforming low-energy electrons from the magnetosphere, initially with energies of tens of electron volts or less, into high-energy electrons capable of producing auroral light, with energies of hundreds of electron volts or more, thereby tapping into a vast source of particles to create the aurora. At times, it can cancel out the current completely, making it seem like there is no electricity flowing through the wires. The aurora borealis appears to consist of electric matter similar to what is produced by an electric galvanic. The currents from the aurora shift along the wires before fading away, with the aurora moving across the sky from the horizon to the zenith. He stakes his claim, then goes to town looking for investors. Jupiter and Saturn both possess magnetic fields that are more powerful than Earth's. Jupiter's equatorial field strength measures 4. By cross-referencing with a map of Mars crustal magnetic anomalies, generated from Mars Global Surveyor data, researchers discovered a striking connection between the emission site and an area of intense magnetic field strength. This correlation strongly suggested that the radiant display was triggered by a flow of electrons streaming along the planet's crustal magnetic field lines, energizing the Martian upper atmosphere. During the years 2014 to 2016, cometary auroras were seen on Comet 67P/Churyumov, Gerasimenko using aboard the Rosetta spacecraft. Researchers credit the vivid colors of the aurora to gases in Earth's atmosphere that become excited. For example, the green hue is produced by oxygen. Researchers utilize satellites to gauge the velocity and thickness of the solar wind, and under favorable circumstances, they are able to anticipate the timing of the aurora borealis. Computer simulations that rely on up-to-date information from diverse tools can also predict the strength and positioning of the aurora borealis. We can put this most simply: find the darkest place you can. Activity starts in the north sky, and depending on strength, can spill overhead into the southern sky. Ideal spot. Start by setting your camera's sensitivity to a moderate level, between 800 and 3200. If your camera excels in capturing images in dimly lit conditions, you can afford to push the sensitivity higher. However, be aware that this may introduce a noticeable texture, or grain, into your photographs. Be prepared to experiment with this setting when you're shooting on location. In order to capture the aurora borealis with your device, you must have the ability to customize the manual settings of your camera. If the default app on your phone or tablet does not offer this feature, you will have to seek an alternative. Adobe's camera app is widely regarded as the top choice for this purpose. Shine on, Keweenaw. By all measures, our epic summers are loved by Keweenaw stargazers and aurora spotters. But the best show may have come when the Perseids overlapped with the Delta Aquarids just as the northern lights began to bloom. The result: this reduction of components results in a more reliable, easier to maintain, longer-lasting unit. Northern Lights marine diesel generators are perfect for pleasure craft and commercial applications. We know that no two boats are exactly alike, which is why we offer custom solutions specifically tailored to your vessel's needs. During intense solar flares, the aurora can be visible as far south as Scotland and northern England, although the majority of activity tends to occur within the designated oval zone. Northern Scandinavia and Iceland offer the most accessible destinations from the UK for viewing the northern lights, but there are recognized locations throughout the zone that offer optimum conditions for sightings. It is important to be away from any sources of artificial light, such as street lighting, whereas you do want to be near open spaces offering big sky viewing. As long as you're within the auroral oval on a clear night between September and April, you can potentially witness the northern lights. That said, it's hard not to get excited by the buzz around the current solar cycle number 25, which started in 2020. Many scientists are reporting that this solar cycle could be one of the strongest on record, a prediction being played out with incredibly strong auroras in 2023. During a new moon the sky is darker, given the perception of more intense displays, but of course the true determining factor remains with aurora activity on any given night. Lunar phases therefore only matter according to personal preference. The lunar cycle has no impact on the frequency or strength of aurora events, but the brightness of the moon can diminish the visibility of the spectacle, especially when viewed without aid.